Welcome back. In this episode, we'll be talking about stylometry, and we're going to start with something that's known as hierarchical cluster analysis, and I'll show you exactly how to do this. We have all of the pieces that we need now to actually start doing this. So to start, we'll import the libraries that we need, same thing that we've been doing before. And if you're interested, I suggest that you go check out brandonrose.com/clustering because there's a good walkthrough of various techniques to cluster documents, and some of the code comes from there. So to do what we need to do in this episode, we'll need to import the regular expression library, NLTK, the OS library, as well as data frames from pandas and NumPy as NP. And once we have these, we'll have all of the components we need. To actually do the analysis, we're going to be importing components from the sklearn library. And we're going to need the feature extraction text, which we've seen already, the TF-IDF vectorizer. And then we're also going to be needing a few things from the metrics library in sklearn. So sklearn.metrics.pairwise, we want, really in this episode, we're only going to be using Euclidean distances, but you can also import the cosine similarity if you'd rather use that. And we'll talk in class about what the differences between those actually are. We also want to actually visualize this to use the SciPy cluster hierarchy, and we'll want to use the linkage module and the dendrogram module, because we'll be using these to visualize the results and conduct the actual clustering of our texts. And of course, we want to use matplotlib.pyplot for the eventual visualization. So to start, we're going to be loading text in from the corpus folder that we created earlier. And I'm also going to add a set that contains files that I want to ignore, because sometimes in the directories that I'm loading in, there are files that will mess up the analysis. So if you're on a Mac, sometimes your operating system is going to create files like dsstore, and if you read these in, the script's going to get a little bit confused because it's not going to be able to accurately compare that automatically generated file with the text that you're comparing. So the vector object wants a list of text, which we saw before, and we're going to prepare for this. So here on line 23, I am just creating an empty list for the texts and an empty list for the titles. And then what I'll do is I'm just going to go through all of the files in the corpus folder, and for every file name in files, and checking, is this file name not in the ignore files, we'll go ahead and open that file as rf, which is, again, the variable name that's substituting for that file object. So what I'll do is I'm just going to say, to this Sherlock Holmes list, go ahead and append the string from the file, and we'll go ahead and make it lowercase because we don't want to deal with the fact that and that's perhaps a bad example, the with a capital T is different than the with a lowercase t. We want to think of those as the same thing. And we want to go ahead and append the file name to the titles. And in this case, I'm saying file name bracket colon -4 to remove the file extension, because I don't actually need that. And we'll make that lowercase as well. So we're going to be using these titles as labels in our eventual plot, but here I have a dictionary that's just going to shorten them, and I type this up manually. You can think of ways to automatically generate a dictionary like this, but for the moment, we're just going to stick with this. So here what I'm doing is, as all of the keys are the names of the files, and here you can see I'm using double quotes because Engineer's Thumb actually has a single quote inside of it. And I'm just going to say I want this shorter title to be Engineer's Thumb. This is just easier to read the eventual graph. Then what I'm going to do on line 41 is I'm going to create a list of shortened titles. So for every title in Sherlock Titles, which is this list right here that we created on line 23 and filled on line 29, I'm just going to feed that title into this dictionary and return the shortened title. So the short titles will just be full of all of the titles, but shorter. So it's a really useful thing to be able to do. Now, I'm actually going to be comparing the frequencies of the 1,000 most common n-grams in this corpus, because common words are often most useful for determining different stylistic differences among documents when you're interested in things like authorship. Now, all of these were, of course, written by the same person, But sometimes there might be time differences or genre differences, and frequent words are often a very useful way of measuring this. Now, you can give this count vectorizer a specific vocabulary if you have words that you want to compare exactly, so you can do that too. But here what we're doing is we're going to create a count vectorizer that is the TF-IDF vectorizer object from the sklearn library. And we're going to say we want to look at the max 1,000 features, and we're not going to use the inverse document frequency. What this is doing is this is just saying, you know, I want just the term frequency. We don't want to adjust it for depending on how many documents it appears in. And that's just a choice. You can play around with this to see if you get better or worse results. Then, of course, we're going to take the Sherlock texts, which are these lists of documents, and we're going to put that into the count vectorizer. And we'll go ahead and fit transform. We've seen this before, talking about just counting up how often words occur. And we'll save this as a count matrix. Now, this is where we start doing the actual stylometric work. Because we have loaded in these document pairwise metrics from sklearn, what we can do is we can use the Euclidean distances function, and we can give it the count matrix. What this will do is this will compare every document in the entire corpus against every other document and return a matrix of information that is how far apart are all of these documents from each other. Then we actually do hierarchical cluster analysis. So what this is doing is this is grouping text together based on which ones are most similar to which other ones. So you can kind of think of it as drawing little boxes around texts that are close to each other, and it uses an algorithm known as the word clustering algorithm. The math is, of course, very important, but for the context of this class, it's maybe a little bit less so. And so what we're doing is we're building a linkage matrix. Then what we can do is once we have all of these different documents clustered together based on the word algorithm, what we can do is we can feed that into the dendrogram function that we imported from SciPy, which is the scientific Python library. We can use the dendrogram function from SciPy to actually visualize this in a dendrogram, which is a tree visualization. And you'll see that here in a second. And I'll talk a little bit about how we might interpret something like this. So what we do is we give this dendrogram function the linkages, which are the connections between the documents that SciPy has created for us up here in line 55. We give it the labels, which are the short titles that we created. And I'm going to add a few extra pieces of information just to make the plot look a little bit better. We're going to make the orientation on the right. We're going to say that the leaf font size is 8 and the leaf rotation is 45. And you'll see what that looks like here in a second. And we can also continue to adjust the plot to make it look a little better. On the x-axis, we actually don't need any ticks, so we'll get rid of these. And we're going to say we don't need labels on the bottom. And then I'm going to call plt.tightLayout to prevent the labels from going off the figure. You don't have to do this, but it makes it look a little bit nicer. So let's go over to our terminal and run this and see what actually happens. So here we're going to, I need to get back into my Hacking the Humanity directory, and I'll go ahead and run this file, which is stylometry1 HCA. So when this runs, it's going to create a plot that looks like this. And so you can see that what it's doing is it's actually clustering documents that, according to the metrics we gave it, are similar to each other. So here we can see that the orange pips and the speckled band seem to be more similar with each other, and then the blue carbuncle. And so what's happening is to read this, you have to follow these paths back. And this junction right here, where these two texts connect together, represents how distant they are according to our metrics. So for example, if we want to think about how similar is the orange pips with the copper beeches, we actually go back out to this junction point right here. And then we find, OK, it's related, but not that related. Now, Bohemia and copper beeches are actually more distantly related than orange pips and copper beeches, because we have to go back to find the first junction between the two. So here, for Bohemia, I trace this out all the way up to this very top level, and this is where these two texts meet, and we trace it back down. So we know that these are not actually that closely related, even though they're right next to each other in our dendrogram plot. Now, we might want to add a little bit of information to this plot to interpret it properly. So what exactly is driving the differences between these two? Now, it's probably content, but what if it's when it was written? Do these texts differentiate between themselves if they were written earlier or later in Arthur Conan Doyle's career? So we can check that by adding a little bit of color to this plot. So let's go back over to our code and take a look at this here. So essentially what I'm doing is I'm doing the exact same thing, except now what I'm going to do is I'm going to add a dictionary here on line 14 that is the year in which the story was written. So I have those short titles that I created before, and I have the year. So Engineer's Thumb was written in 1892, The Red-Headed League was written in 1891, and so on and so forth. And I'm going to create a dictionary that gives us a color for each year. So let's just make all of the texts that were written in 1891 magenta and all that were written in 1892 green. So this will let us create that exact same dendrogram, but add color so we can interpret it a little more easily. So all of this is the same. We keep going down until we get to line 52. So here we've done our tight layout thing. Now we want to go back in and change the color of our labels so we know what year these texts were written in. To do this, we need an access object, which we get by calling plt.gca. And then what we can do is we can actually use this AX variable, and this of course could be any variable that you name it. It could be George if you wanted. So we say ax.get y major tick labels because those labels are on the y-axis, and this is a method. And we'll save this as the labels. So now this labels variable gives us access to these tick labels, and we can change them around. So what I'm going to do is I'm just going to go through every label in the labels, and I'm going to set the color. And here, this looks a little bit funky here, but it's relatively straightforward. So I have the year color dictionary. So essentially, what this is eventually going to give me is a color, either magenta or green. Then what I need to do is I need to take the story year to get the year, and I'll take the label and I'll get the text from the label. Because if you remember, the text that is being used as a label are just those short titles. So essentially, this is Engineer's Thumb into the story year dictionary, and then the story year dictionary value into the year color. And this will set the colors. So what I can do is I can just go ahead and run this, and we'll go back here and take a look at what happens. So now what we have is the exact same dendrogram, except now the labels are colored based on the year. Now, looking at this, it doesn't really seem like this is a good way of interpreting the differences between these particular texts. And it's entirely possible that there's not a meaningful difference stylistically between these, and this is what I would lean to. So we should actually look at a specific case where the differences are actually meaningful. So I want to turn to the next script. And this is a relatively famous example of the application of stylometry. So let's apply this to a real-world problem, the Federalist Papers. Now, the Federalist Papers are very famous as an authorship attribution problem because they were written anonymously by Alexander Hamilton, James Madison, and John Jay, defending the new US Constitution. And the authorship of 12 of these are disputed, numbers 49 to 58 and 62 and 63. The reason is Alexander Hamilton claimed he wrote these 12 Federalist Papers in his journal shortly before he died. But all evidence suggests that it was in fact James Madison who wrote these 12, or possibly a combination of Alexander Hamilton and James Madison. Now, most scholars had traditionally thought that Madison actually wrote these, or maybe together with Hamilton. But scholars wanted to come up with ways of evaluating this mathematically, and in the 1960s, Frederick Mosteller and David Wallace decided to do exactly that. And so here we're going to do a basic recreation of their experiment. only now we're going to be using the Federalist Papers instead of the Sherlock Holmes short stories. So what we need to do is we need to actually open the text and read it into our program. Now, I downloaded this from Project Gutenberg, but I should point out that the Project Gutenberg version actually has two versions of Federalist number 70. So for simplicity's sake, in the code and the documents that I provided as part of this course, I've removed one. So what I'll do is I'll just open up the Federalist and as RF, and I'm going to read it into a text variable, and then I'm going to close it. I'm not using the context manager like I have in other exercises, just for simplicity's sake here. So the first thing I'm going to do is I'm going to remove the end boilerplate. I don't really need the end of the Project Gutenberg text. And then what I'm going to do is I'm going to divide the text based on internal divisions. So what I'll do is I have this variable that I'm going to call papers. So I'm going to use regular expressions to split these texts apart. And this is a fairly basic regular expression in which I'm saying, I know that this is the pattern that matches the dividing lines between all of these different papers. So I'm saying Federalist \period. So I know it's Federalist with a literal period, sometimes but not always, which is why I have this question mark. And then a space, and then number \period because it's a literal period, which is optional, and then a space, and then a number. So what this will do is this will split it along these Federalist headings. Then what I'm going to do is I'm just going to use this papers bracket 1 close bracket to delete the first item in this list because there's actually nothing useful before the first Federalist paper in terms of the analysis that I'm doing. And here I printed out just to make sure that I actually have 85 items. So then what I do is I just create a list that has a number for each of these Federalist papers. And I'm not going to start at 0 because there is no Federalist 0. So it's just 1, it's I plus 1 for I in range the length of the papers. And we've seen this construction a few times in this class now. So the next thing I want to do is I want to create a dictionary with the authorship information. So here I'm saying authorship equals an empty dictionary, and then I'm just going to go through each item in the Federalist, each item in this list of Federalist papers. And I'm saying FNO, which is just the Federalist number, equals I plus 1. And here what I've done is I've just put together a relatively basic piece of logic that ascribes the authorship of individual Federalists according to who wrote them. So for numbers 10, 14, and 18 to 20, and 37 to 48, I know that James Madison wrote these. So I'll go ahead and say for the Federalist number, save Madison as the author. I know that John Jay wrote Federalists 2, 3, 4, 5, and 64. And I know that these are the unknown ones, and everything else was written by Alexander Hamilton. Now the next thing I'm going to do is I'm going to go ahead and ascribe a color to each of these authors. So anything written by Hamilton is going to be in magenta, anything by Madison is green, anything by John Jay is brown, and the unknowns are just going to be black. So I'm going to go ahead and do the analysis. The rest of this code is just exactly what we saw in the previous example. So let's run this and see, does this give us what appears to be a meaningful result? So stylometry 3, Federalist. So we'll go ahead and run this. And what it does is it gives us this as the result. So I'll go ahead and maximize this so you can see. And you can see this is a little hard to read, but this is actually a really great result. So let's look at these. We know, for example, that John Jay wrote 5 of these, and John Jay is way over here in the corner all by himself. And this is a really, really good result because here, John Jay is very different than Alexander Hamilton and James Madison. Now, the unknown texts are in black here, and we can in fact see that all of these, or rather most of them, are clustered together with other texts written by James Madison. And here we can follow these dendrograms out, and we can see that number 44 right here is not actually very close in the dendrogram to 33, which actually joins up back here. So we can see, in fact, that for most of these, they really look a lot more like James Madison's writings than they do Alexander Hamilton's. Now you'll notice there are a few things going on here. For example, we have a few James Madison texts down here and a couple interspersed in here. And that's because when it's not done in a very refined way, sometimes we get a lot of extra noise. You can refine this to try to get all of Madison's works together, but in some cases these may be co-authored, so this isn't a too surprising result. So this shows you that hierarchical cluster analysis is actually a really interesting way of trying to group text together by authorship. Now, this is not always going to give us accurate answers, and sometimes it might mislead us into thinking that we have definitively shown authorship based on math, but it is fairly suggestive. So to me, this is a really cool result. In the next episode, we're going to be talking about the same sorts of techniques, except instead of using hierarchical cluster analysis, we'll be using principal component analysis. So I'll see you in the next episode, and thank you.